faculty at Ithaca College. He studies the formation of exoplanetary systems using observations of dusty material orbiting young stars called circumstellar or protoplanetary disks. He uses data from the Spitzer Space Telescope and the Hubble Space Telescope. He's developed instrumentation for several astronomical telescopes. He was a co-investigator on a team that built an infrared camera for NASA's Airborne Stratospheric Observatory for Infrared Astronomy, shorthanded as SOFIA, thankfully, which flew missions from 2010 to 2022. He worked on the optical system for the SOFIA camera and led development and construction of an upgrade enabling spectroscopic observations. He regularly serves on review panels for NASA and other scientific agencies. In parallel with his scientific research and engineering work, he's written articles and essays for science communication to the general public. And he's worked on several projects integrating science with art and performance. And he's here today to answer the question I asked him last fall when we ran into each other at a conference meeting at Ithaca College. How do people down here know what's up there? And so he's going to hopefully answer my question. So help me welcome Luke Keller.
Thank you. Thanks so much. I love this. It's like students, faculty, you students here. I didn't know whether there was going to be like lobbing things across the room.
Good, could happen.
Comes later.
Yeah. So today I'm going to tell you the story of planet formation. You may have heard this story before. But in particular, as Marion said, I'm interested in telling you how we know all of this, which to me is the more important question. So I have some cartoons. They're not really mine. They were created by another astronomer. But this tells the story, and it starts with a collapsing gas cloud, a big collapsing gas cloud. And you can see that I put a little scale on there, about a light year or several light years across. We're talking the Orion Nebula, if you're familiar with objects in the sky. And gravity collapses this cloud, condenses the gas and dust, and we start the clock, t equals 0. That's time equals 0. And then 10 to 100,000 years later, this, what used to be a cloud, has collapsed. And since clouds swirl as you collapse them, just like when you see a gymnast or a skater start spinning and then they pull their arms in and they spin faster, what happens is some of the material gets flattened out into a disk. Have you ever seen somebody making pizza crust and they throw it up in the air? Same thing. And then the condensed material in the center heats up. It's called a protostar. Proto is almost. So you are proto-college graduates. And you can see the yellow stuff. There's a jet. So this is a very, very active process. And the interaction of gravity and magnetic fields and the motion of very hot material ejects some of that material out the top and out the bottom. And we call that a protostar and a protostellar disk. And it's in the disk of material that orbits that newly formed star that we get the planets. So the planets form from the exact same stuff that the stars form from. So everything that is in our solar system now was in the cloud that formed the sun. Next stage, active protoplanetary disk. You can see the time is now 3 to 20 million years. And the reason there's such a big range is because the time frame for this depends on the mass of the original cloud. So the bigger the cloud, the faster it happens. And that stage on the left is what my students call the fried egg over easy stage. You see the star in the center, but it's really surrounded by a lot of stuff. And the stuff goes straight into the star. So we call it an active disk because it's actively accreting or gathering material from the disk onto the star. So you know that our sun has sunspots. Young stars have really big, really active sunspots, really active star at that stage. And then eventually, the material gets swept up by condensing objects that will become planets. And those are protoplanets. And you get this ring system, and eventually just planets with a little bit of dust and things like asteroids and comets thrown in. Okay, so that is the story. But how do we know this, right? How do you figure this out? So I want to start with a little bit of an overview of what we can measure in astronomy just in general. And first, we can look at the processes, so physical processes, how this might happen. How might a disk of material, mostly gas and dust, form planets? And there are two processes. One's called core accretion, and you probably heard about this. This is where little dust particles stick together to form sand grains, and then those stick together to form pebbles, and those stick together to form rocks, and then boulders, and then asteroids, and pretty soon you have Earth. Or the core of Jupiter, perhaps, if it has a solid core. The other, I have an animation, is gravitational instability. So this is the disk, and you can see that there's a little knot of material here orbiting the star, which is that little tiny point right in the middle, and gravity is actually gathering gas to form a much larger object, kind of like maybe our planet Jupiter or Saturn. And we think, those of us who study this sort of thing, it's probably both processes happening. It may be that the core accretion creates something like Earth, and then its gravity gathers gas into an atmosphere. That may be what's going on. And you can see as the planet is forming, it's clearing out a gap in the disk. It's using up material. Okay, whoops, too fast. Can't go backwards. Well, it said, how do we know this? How do you know anything in science? You make measurements. You observe. In astronomy, we can only observe, right? The things that we're studying, unless you're studying our solar system, where we have, I always say, my colleagues who are planetary scientists have the luxury of being able to send spacecraft out to all, we visited all the planets, we visited asteroids, we visited comets, and they can actually now go pick up a piece and bring it back and have it in their laboratory. It's like not going to happen with even the closest star, and it's not even going to happen with our sun. Try to go take a piece of the sun. So here are the things you want to know. They're things that if you just went out on campus and asked, so what do you want to know? What would you want to know about stars? They would be things, I won't read them all, you can read. How big is it? How hot is it? How far away is it? Where did it form? How long ago was that? Could it ever kill me? Like, is it dangerous? What if it exploded? These are the things we want to know. But in astronomy, astronomy outside of our solar system, it's an observational only science. That means we can't do experiments. Now, some definitions of the scientific method require us to do repeatable experiments. That ain't possible in astronomy because we don't have control. You can't do a controlled experiment because we have no control over the systems that we're studying. So we can't say, okay, I'm going to take a star, set it aside, and then take this other star that's identical to it and mess with it and see what happens. It can't happen. So what we can do is look. So here are the things that we can do in astronomy. We can see where things are. It's an apparent position. Those two stars look like they're there, but who knows why why the one on the left is fainter. It might be intrinsically fainter, or it might be farther away. Or there might be a dust cloud between us and that star making it look fainter. So this is apparent position in the sky. From our point of view, apparent brightness, once again, some stars look faint, some look bright, but that's an apparent property. Just by looking, we can't tell why they're fainter or why they're brighter, only that they look that way to us from our vantage point here on or near the Earth if we're looking through a space telescope. Apparent color. That's also an apparent property. It looks colorful, looks like it has all the colors in the rainbow, but the color could be altered by the environment between us and the object as well. Apparent size. How big is it? Well, the moon looks like it's a little bit smaller than the Empire State Building in this picture. We all know that's not true. But if you didn't know that's not true, it would be a perfectly good assumption, a perfectly good conclusion from this observation. Shape. Spiral galaxy. What would happen if I looked at this galaxy from a different position, though? If I looked at it from the bottom or from the side, it would look like a flat disk. It's like a pizza. right? It's flat. But from this vantage, that is not apparent. And we can also observe the stuff that it emits, mostly light, the electromagnetic spectrum, but things in space also emit particles, the kinds of particles you're familiar with, atoms, electrons, protons, and we now know that they also emit gravity waves, waves of space-time curvature, which will be a whole other talk. And there are observatories that observe all of the electromagnetic spectrum, usually not the same observatory, but many together. And it's from these observations that we can gather the information that we need. So I made a list. I like lists. If you ask my students, they're like, Luke likes lists. All right, so on the right is the stuff we want to know. On the left is the only things that we can directly observe. And the interesting thing for me, one of the interesting things, is that those are all things we can observe with our senses. Like that's how we experience the world. It's also how we experience the universe. But when you hear in the news or in a class, the James Webb Space Telescope has just shown us that we don't know everything we thought we did about the Big Bang. That sounds like we measured something about the Big Bang. We don't measure the Big Bang. We don't measure star formation. We don't measure the physical properties of these systems. We measure those things and the one at the bottom, how they change with time. And sometimes you can actually watch objects in space change with time. Sometimes the time frame is shorter than a human lifetime. Most of the time it's not. Oh, and I'm a professor, so raising hands and saying, hey, I have a question is okay. Don't have to wait till the end. All right, how do we get from the left to the right? Scientific method, right? The same scientific process that you've learned and that you know and love in your lab classes, that's how we'll do this. Which constellation? Orion, yeah. Orion's one of the easy ones to spot because of the three pretty close brightness stars there in the center, the belt of Orion. And if you look just below the belt of Orion is this group of stars here that includes kind of a fuzzy one, which is the Great Nebula in Orion. That's what it looks like through a telescope. And that is one of those clouds that is now forming stars. I love this. It is forming stars now. Like this is not, and you've heard, I'm sure, of cosmic look-back time, or maybe you haven't heard it called that. It's where when you look at things out in the universe, you're seeing them as they were in the past. We are seeing this as it was in the past, but only 1,500 years ago. And in the time frame, remember the time frame of the formation? That's nothing, right? It is like that now, and it is forming stars now. The stars that we see in the center, if we zoom in even more, that's a James Webb Space Telescope picture. So this would be an infrared. Those stars, most of them are less than 1 million years old, which means when they formed, there were people on this planet. That's pretty young, because stars can live to be, well, the sun is 5 billion years old and probably go another 4 billion, so pretty young. We go even farther, we start seeing objects like this. Looks like a UFO, right? It's one of those protoplanetary disks. We're looking at it from the side, and you can see a star, and it's obscured by the dark is a silhouette of the disk. We're looking at it from the side of the dusty disk, and we see thousands of these things. So how do we figure this out? One way we figure this out is to make a computer model, a simulation of the process of star formation. You have to tell me when you start seeing stars, by the way. And this is a density map. So yellow and white are much, much more dense. That's where gravity is really condensing the gas. And that's where we're going to see the stars form. So they'll come flying out of the yellow stuff. And by the way, this is about 2.5 light years across. And it has the mass of about 500 suns, all of the gas in this. All right, there you go. When I first saw this simulation, it was in a meeting in a room about this size, actually a little bit bigger, full of professional astronomers, and we were going, oh, there's one right there. And what really was amazing to me is how they're moving. which is pretty cool. Stars are moving when they form because the cloud was moving that they formed from. All right, so we formed a cluster of stars. And this is a simulation. I have to make the distinction. So this is computer graphics. It's a simulation, which means that some physicists and computer scientists wrote a computer code that is a model of the process of star formation. So Newton's laws of gravity, fluid dynamics, how a gas interacts with other gas, magnetic and electric fields, how they affect the motion of gas and the interaction of atoms. All of the physics and chemistry that we know programmed into this model, and then put 500 suns worth of it, hit return, and wait for a supercomputer, in this case for a year, to crunch the data, and then out comes a movie. It's not like special effects, where you do the same thing, probably the same computer scientist and the same physics and chemistry, but in that case you say, you know what I would really like is for this cloud to do that. Can you make this cloud do that? And they say, of course we can, we're making a movie. In this case, we say, I wonder what's going to happen to that cloud when we hit return. That's a simulation. And then we have a model, which we can now compare to the things that we observe in space and see how accurate our model was. And here's the observation. So these are all real images, real observations. The wispy stuff is the cloud, and that is a radio image. So it's radio waves coming from mostly atomic hydrogen in the cloud that is creating these stars by gravitational collapse. And then the little insets are radio and infrared images of the little spots that appear. And some of them look like disks. Some of them look like a little bit like a spiral, like that one there. So the question is, when those little stars popped out of the simulation, maybe we could zoom in and see what they actually look like, what the material around them looks like. Here's some other real images from the Orion Nebula. As I said, and this is just a few of the little protoplanetary disks that we see. So essentially what we see is all the young stars, all of them, have a disk around them, have material orbiting. All right, this is the same simulation that we just saw, but every time a little square pops up, it's following one of the stars. 187 stars formed in that simulation, but it's zoomed in. Each of the squares is about the size of our solar system. So you see a little star, they're moving around, and they have disks, spirals, and basically each system shows up on the screen now as it is formed in the original simulation. And I talked to Matthew Bate, the person who wrote the code. That's how I know it took a year for the code to run. And it just keeps going and going, and we get a couple of hundred stars. And what we want to do is look at the structure of the material around the star, because we can, for some systems that we study, actually see them in this much detail. And we're going to compare it and see if we see what we predicted with this story about how planets form. So there they all are. And some of them, in the time that it took for the model to run, which represents about 200,000 years of real time, you can see some of them are just a star. They dissipated all of the gas and dust. And the model does not have enough detail to zoom in and see if there are planets there. That one would take 100,000 years to run. These are real images of protoplanetary disks. So these are radio images. We now have radio interferometers, mini radio telescopes working together that can form an image. And so this is relatively warm material. So it's not the star. You don't see the star in the middle. What you see is all the dust surrounding the star. And we can see the structure that dust forms. And we see spirals, sets of concentric rings. Some of them are double. That's a double star. Two suns. So if you're in planets orbiting this star, you have this other star right nearby. There are actually triple systems. And if you zoom in on some of them, they have, so in this one, you have this very kind of faint blob, but when you zoom in, it's one of these condensations. So it looks like the simulation of gravitational instability. So we're starting to see examples of real life systems that very closely, that our models very closely resemble. So that doesn't mean we're right. That means we can have a little bit more confidence in our model because it matches what we actually observe in the universe. And that's just allows you to compare the models, some of the models, with some of the actual systems. And you see similar structures, spirals, concentric rings. And we remember one of the final stages of the planet formation process, you have a disk that has gaps in it where the planets are forming. Now, I was at that conference, this was 2016, a conference of astronomers and students, mostly professional astronomers and their students, about 150 of us. And when this picture came up, this was a new telescope. The Atacama Large Millimeter Array is a radio telescope that took these pictures. When this came up on the screen, it was a graduate student from Harvard giving one of her first talks. The place went nuts, right? Phones out, people screaming and talking. It was amazing because we had spent 20 years wondering, predicting that we would see concentric rings and spirals, but had never seen them before. And that was the first release of those data. So my students don't believe me. Like a bunch of professors got all bananas over dust. Yeah, that's what happens. Okay, so now I can go through that same cartoon much, much faster, but now we have pictures, and we have lots of pictures of each of the stages. So you have a collapsing cloud, you have the disk with the jets running out of it, the fried egg still looks like a fried egg, and then we have the concentric rings as the planets begin to form. So that's pretty cool. So one of the answers to the question, how do we know how planets form, is, well, we can take pictures of them at various stages. So this is, if you notice at the top, the year is counting up. These are all of the exoplanets that we have identified in the Milky Way galaxy. So planets that are orbiting other stars. It'll just play over again. So starts off in the 90s, and then through the 2000s, it just gets more and more and more and more. And then right here, that was a spacecraft that got launched that all it did was look for planets, but only in a very small part of the galaxy. And you can see that we see lots and lots of exoplanets. Some of them are close enough to take an image a few times a year, in this case over 12 years, and make a movie of a solar system. So the star has been blocked out. It's at the position of the star icon, and you can see the planets actually orbiting. There are, at last count, I think 3 systems that are close enough that we could do this. I didn't help, we astronomers, right? Most of the protoplanetary systems, the systems that are forming planets, are so far away that when you take a picture, even with the James Webb Space Telescope, they look like a fuzzy dot. Like you can't see the disk, you can't see the concentric. Question?
Yeah, I have a question for you.
Yeah.
Really fascinating. The previous slide you showed all the exoplanets. Is that exoplanets that are being formed or that were just discovered?
They're just discovered. They're already planets. And the question is, so these are 2 fields of astrophysics that have been going kind of in parallel, like looking for exoplanets and trying to describe how planets form. But now we have so much information in both that they're coming together, and we're starting to say, okay, we have exoplanets. In fact, my next slide is, this is a website you can go to, the Exoplanet Archive, and as you can see on, what was the date? 3/26/24, so just a week or so ago. 5,602 confirmed exoplanets, 432 TESS confirmed. TESS is a new spacecraft. All it does is look for exoplanets. It's working now. And it has found over 7,000 objects that need to be confirmed. And the question, now we can get, excuse me, now we can get statistics.
We have planets that have all different masses, different sizes, different compositions. We can measure the composition of their atmospheres using spectra. And that helps us with the formation, those of us who study the formation process, because the formation process has to produce the planets that we actually observe. Like if we're right about how planets form, then we should be able to predict that they'll form the variety of planets that we actually observe, because that's how science works. Okay, details. Like we know that we're pretty sure we have evidence that that cartoon version of the story is the way it happens. But like exactly how does it happen? Does it always happen? Do all stars have planets? That's a good question. We think so. It's looking like it. Okay, so this is information you can impress friends at parties. So we have almost 14 billion years to work with, apparently, of the universe. I call it the small flash because it was neither big nor was it a bang. The Milky Way galaxy formed somewhere around 11, 12 billion years ago. Sun, much more recently, almost 5 billion years ago. And then the planets form right after the star. And they did in our solar system as well. The fun fact is the Earth is a third the age of the universe. I at least, before I kind of appreciate it, I won't tell, it's embarrassingly recently that I appreciated this fact. I knew this fact, but it didn't really occur to me to think, wow, 1/3. You think of the universe as just vastly old, and the Earth must be really quite recent. But we're not. We're pretty old. Okay, so as I said earlier, mentioned, we know of thousands of planets. We also know of thousands of protoplanetary disks. They're pretty easy to detect. They're really difficult to see, to actually look and see their structure, because most of them are way too far away. And in fact, I don't know what the last count is, but it's 4,000 or more. But only a few are close enough. In fact, that image that I showed with 25 protoplanetary disks, that's basically the 25 that are close enough to make an image like that. So that's it. Unless we build a radio telescope the size of maybe like the orbit of Mars, that would be really cool. And then we can make better, more detailed images of the systems that are farther away. Okay, so here's a little bit of the research that I do. This talk is not about the research that I do. It's about the field that I participate in. But what I'm interested in is a question that one of my students asked me a long time ago, 15 years ago. She came up to me. It was an intro astronomy class, not a science major. Like, what were the first planets like was the question. And so I started to blah, 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 professor. First you get a cloud and it collapsed. And she's like, no, I know that. I want to know what the very first planets looked like in the universe. Were they like Earth? Were they like Jupiter? What were they like? And so I said, in my head, I don't know. To my student, let's Google it. And I Googled it, we Googled it, and it turns out at the time, no one knew what the first planets were like. We still don't know what the first planets are like. And thus was created my life's work for the last 15 years. So unfortunately, in order to observe planets forming in the early universe, you have to observe galaxies in the early universe. What do those look like? What do the James Webb pictures of the earliest galaxies look like? Do you happen to know? Has anybody seen them? I should have put a picture up here, but I didn't think of it. They're little red fuzzballs. A whole galaxy of several 100 billion stars is a little red fuzzball. So there's no way that we're even going to image individual stars in that galaxy, let alone little disks around them. So that's out. We can't actually, at least not now, directly observe the first planets. So what we do instead is look for galaxies that are much closer to us, that have the same chemical composition averaged over the galaxy that the early galaxies had. And there happen to be two of them very close called the Magellanic Clouds, only visible in the southern hemisphere, and there they are right there. Astronomers, you might know, are very creative when they name things. So this is the large Magellanic Cloud, and this is the small Magellanic Cloud. The small Magellanic Cloud has 1/5. If you measure what we call the metallicity, we can't get into this. Astronomers and chemists don't get along sometimes. Astronomers think anything heavier than hydrogen is a metal. And the metallicity is the ratio of hydrogen to the heavy elements. And in a more advanced or more processed, evolved galaxy, stars have created more of the heavy elements, so that ratio is one value. And in the early universe, when it was mostly hydrogen and helium, that ratio is very, very different. The small Magellanic Cloud has 1/5 of the heavy elements that the Milky Way does. So the small Magellanic Cloud, the environment there for star and planet formation is like our galaxy several billion years ago. So it's kind of like the early universe. So the picture, the inset picture, is a negative picture. So black blobs are nebulae. These are forming stars, but the black means bright. And the ones with numbers on them are the objects that I've been studying for the last 12 years. And they are objects that appear from their colors mainly in the infrared to be protoplanetary disks, but we can't take a picture. And I'll give you an example. So this is an image of the entire small Magellanic Cloud, so an entire galaxy. And we're going to zoom in this is a visible light picture. We're going to zoom in to one of the objects that I study. There's a little green circle around it. 4 pixels. That's what we got. So, I mean, at least it's distinct from the other stars, right? But that's it. And then I thought, I had a student about 5 years ago who was interested in this question of, what if we're not looking at what we think we're looking at? Like, this is really far away. Those 4 pixels are the size of the center of the Orion Nebula. So she looked in the Hubble Space Telescope archive. So you may or may not be aware that when NASA spends billions of dollars of taxpayer money, they're required by law to let all of us have the data. And it's called an archive, a data archive. You can go to the Hubble Data Archive and pull down all sorts of interesting information. And so what she did was to put the coordinates of each of our objects and see if somebody had inadvertently observed our objects, right? Because they're taking great big pictures of space, and sure enough, they observed that object. They were looking for something completely different. They were looking for dying stars. We're looking for stars at the beginning of their life. But thanks, right? And here's the Hubble image. "23 stars in those 4 pixels. So a whole group of collaborators all over the planet in this project that I work on now have to explain, well, which one of those is the one that we have the spectrum from? Or maybe it's all of them, or maybe it's just some of them. Those stars probably formed together in a nebula. So they have the same chemical composition, but they're not the same mass, and therefore they're at different stages of their evolution, of their lifetime. So maybe some of them are forming planets, maybe some of them have already formed planets. We don't know. But I'm sure you've heard a scientist say, or a professor say, the cool thing about trying to observe something that nobody else has observed is that when you finally get the data, it often raises more questions. It's kind of like job security for astrophysicists. So now we have 23 objects to study and try to figure out which one is forming planets, if any of them. Unfortunately, only 2 of the objects that we study were serendipitously observed by the Hubble. So we have to apply for observing time to use the telescope to try to get a little bit more. Okay, so we can't make an image. So we have to have another technique to learn about these systems and try to figure out if they're forming planets or not. So there's the picture. This is one of my favorite quotes from one of my professors. So a spectrum has a lot of information in it. and it has information about the chemical composition of whatever you're looking at, how dense it is, what its temperature is. You can figure out all of these physical characteristics that we care about from measuring a spectrum, and so that's what we're doing. Since we can't make an image, and you can make a spectrum pretty easily, right? Just pass the light through a prism or a diffraction grating, and it forms a spectrum. This is the lamp in my lab. And then you can make a graph of brightness of each color versus wavelength or color, and that allows us to be quantitative about the relative brightness of each of those features, which we can use that information to get those chemical compositions, densities, and those sorts of things. So here's what it looks like if you want to take a spectrum of an object that's 180,000 light years away, which is how far away that little blob was. You have to put your spectrograph, which is a prism and a camera, onto a telescope, and then it takes a picture of the spectrum instead of a picture of the object. And then we make the graph, because as you can see in this graph, this is a graph of the Orion Nebula. You can see that the features that indicate different atoms and molecules have different brightness, different heights. And that's information that's useful to us. So this is an artist's picture, what a protoplanetary disk might look like if we could jump in your favorite spacecraft, what, Millennium Falcon, you name it, right? And go right there and take a picture. We can't take this picture yet. And what we're going to do is look at one side. So what we can see there is the star is obscured, and there's dust, which is the dark stuff, and it's a ring. It's like a donut around the star, and we're looking at it from the edge, so we can't really see the star. And I want to focus on just one side of it and make a cross section, like chop the donut in half and see what's inside. So there's a cartoon of what's inside. So we have the star, and then we have a disk, which is the dots represent dust particles. Not enough in my picture, but that's what they represent, is where the dust is in this. And then the faint blue is the gas, which is mixed in, hydrogen mostly, but also helium, oxygen, you name it, gas. And the star, the red represents stuff accreting onto the star. These arrows are starlight illuminating the disk. And one thing that you can see is that the disk gets thicker as you go farther from the star. It's called a radial flare, which I think would be a cool name of a band. And with time, what happens is with that, the dust particles coagulate, and they get heavier, and they fall due to the gravity to the center, the midplane of the disk, and pretty soon you have just the gas gets evaporated. EUV stands for extreme ultraviolet. So ultraviolet from the star is evaporating the gas and some of the dust, and you get big dust particles. And then eventually just really big dust particles, otherwise known as planets, and not very much gas or dust in between. So that's the cartoon version again. We actually do observe these different stages. And these are actual pictures from the James Webb Space Telescope. The one on the left is edge on, and you can see, kind of see, the radial flare. You can see that the dark part gets thicker as it goes out. But this other one is actually getting thinner as you go out. So the one on the right is a later stage, according to our picture, of how these systems evolve. And the stuff has fallen down to the plane of the disk instead of floating up above it. And the size, you can see, Neptune's orbit in our solar system is that big. So about the size of a solar system. Okay, how do we figure, so we can't make this picture though. Can't make any of the pictures except those pictures, these pictures here are real pictures from James Webb. But those are only the closest objects, and we have thousands of these things that are too far away to make a picture like that. So what we do instead is make a spectrum. And we can infer from the shape of the spectrum an awful lot about these systems. For example, just a star, this is in the infrared part of the spectrum. So visible light in this spectrum graph here, the visible part of the spectrum would be over here, and the radio is over here. So we're infrared. In the infrared, a star would just start bright at short wavelengths and get fainter towards longer wavelengths. A star with a disk that goes all the way to the star, a disk of luminous dust, there's what the star would look like without the dust, and there's what it looks like, what the spectrum looks like with the dust. So this warm dust is emitting a lot of infrared. We call this an infrared excess. That means it's emitting more infrared than a star should, from which we conclude there must be something else there. And it's dusty. And when you take a picture of it, it's a teensy-weensy little star. So that stuff is very, very close to the star. That's what we can assume. And then if there's a gap in the middle between the star and the disk, what you see is some of a star spectrum and some of a disk spectrum, kind of a mixture. So we can tell just by what the spectrum looks like, sort of qualitatively, we'll start to be able to talk about the structure of this system. So here's some real data. My clicker's getting tired. There we go. Some real data from one of our studies, which shows the full, almost the full electromagnetic spectrum. So this is ultraviolet here, visible light, infrared, and getting long infrared almost to the radio waves there. So not really a spectrum. Actually, there are spectra in here. So this curve is what the star would look like just by itself. The blue is an actual spectrum in visible light of the star, which we did from a ground-based telescope, a telescope in Australia, because these objects are only visible in the southern hemisphere. And then the red is a space telescope. Spitzer Space Telescope preceded the James Webb. It's now not working anymore by design. It had a lifetime. In order for it to work, it needed to be extremely cold, which meant it needed to have liquid helium aboard, and the helium all boiled away, because it's really hard not to boil away helium when you have a sun-like star shining on you. And then the diamonds are individual, we call them photometric observations, just how bright is the object, but not really a spectrum. But when you put them all together and connect the dots, what we see is an excess. So some stuff orbiting this star. And there are actually two of them. This object looks a lot like that spectrum, and this object, you can see how it follows the star spectrum here. That looks a lot like this. So probably this object is farther along in the process, and it has cleared out a gap in close to the star. So here's what we can tell. That's one of the spectra again, and then our cartoon of the object. And we can see that the light from the star, we get ultraviolet and visible light. That's all coming from the star. The inner disk right here that's heated up a lot by the star, it's very warm. By warm, I mean a few hundred Kelvin, up to 1,000 Kelvin maybe. That comes out in the infrared. That's glowing in the infrared. So you see that in our spectrum right here. And then keep going out farther in the disk. The stuff that's floating above and below the center, we see that in the Spitzer spectrum. And by the way, those little bumps and wiggles are from dust and hydrocarbon. So carbon and hydrogen molecules. And then finally, the cold material that's in the plane of the disk that's hidden from the star, we'll see that in the radio. So somebody who's practiced at interpreting these spectra, when I look at this, I see this. Right? We can actually, from the structure of the spectrum, from the relative brightness of the different features, figure out what the structure of the system is, even though we can't take a picture of it. How do we have confidence in that process? We can take spectra of the ones we can take pictures of, and they match. So we have pretty high confidence that this technique, which is the only one we have at our disposal right now, actually does work for the closer objects. And then I just have a few, finishing up here, just a few images to show systems. There's a ring. You can see the ring. This is a radio picture. So there's the stars in the middle. You can't really see it. And there's an object right here, which is a planet right there, a planet that's still forming. But it's in the gap where the planet would have used up all the material. And actually, James Webb Space Telescope, one of the things that it can do really, really well is take spectra that are really detailed. And so this is a spectrum that shows that there's water in the vapor form, gaseous water, in this disk along with the dust. That's how we got oceans, by the way, was water in our protoplanetary disk early on. Here's another example, a water spectrum. So the spectrum, all the blue filled in features are features from H2O. And I'll just come back to the theme, right? Now you have some examples of how we take the relatively mundane and boring things that we can actually measure to try to figure out the more exciting and interesting things that we want to know. And then I end with my current favorite James Webb picture, which is a nebula with a great big cluster of newly formed stars in the center. And you can actually see there's kind of a bubble. It's cleared out the material where those stars formed. That's it. Thank you. Thanks. Question?
Okay, so I'm still interested in what your student asked you 15 years ago.
Mm-hmm.
And you're trying to match up the small Magellanic Cloud with very early galaxies in the early universe.
Mm-hmm.
So there's a chemical matchup. And what I'm primarily interested in is how far, so obviously as stars, well not obviously, you and I know, as stars get older and then have a supernova,
Mm-hmm.
the size of the elements go further up the periodic table. Right? So water and carbon were both mentioned as being present in the small Magellanic Cloud, presumably also seen in those early universe.
Yes.
So the kind of solar systems that you are interested in finding, am I right in assuming that they will have only the lower elements? And
Correct.
have you figured out how far up that goes?
Yeah, we're still working on that, but
You could imagine the very earliest planets would have been formed around stars that just formed from hydrogen and helium. So probably they wouldn't have planets at all. There would be no dust at all, because for dust you need silicon or carbon and oxygen and hydrogen, the things that make up dust. But then those stars explode, they create heavier elements, you form stars from that stuff. So stars are great at recycling the periodic table. That's what they do. And so you have now a little bit more enriched, a little bit of dust. And so probably what happens there is that you form huge planets, like Jupiter, but 100 times, almost 100 times. If it gets 100 times Jupiter, it becomes a star itself. So very large gaseous planets. So unfortunately not Earth-like. And then as you go later and later in the universe, it becomes chemically more like us. And therefore, we would expect the solar systems to be more like ours.
So the small Magellanic Cloud looks like
It looks like about halfway back.
so
like
so
4 or 5 billion
5
years.
billion years. Right.
And from what we see here, it looks pretty similar to the systems that are very close to us. So we're looking for very subtle differences. Yes, Mary.
In the simulation of the formation of stars, two related questions. One is, in the simulation, just showing things forming and moving out. A, what happens? Why do they move out and not just stay stagnant? The second question, do any of them accrete with one another?
Yeah.
As they-
Okay, so this is the cloud collapse and all the stars start going ping, ping, ping. The reason that they're going out is because the gas that they collapsed from was moving. So they're just moving in the same direction that their little cloudlet was moving. Also, they interact with each other and slingshot out. And so the sun would have formed in a cluster like this, and it's now the beautiful stars that we see at night, some of them, right? They've moved out over billions of years. But some of them do actually get together and form doubles and triples even. of star systems that have more than one. Yeah. Other questions?
So given the number of planetary systems found so far in the galaxy, which I think you said was 5,000 or 50,000?
A little over 5,000 confirmed.
What's the current estimate for what is the likely number, given that that's just a statistical sample?
The likely number in the whole galaxy?
Yeah.
Billions.
So basically,
Billions of
there'll be
planets.
several for every.
Yeah.
I mean, the current reasoning is several for every star.
Yeah. Okay. Yeah. The current from that statistical sample, most stars, if not all, have planets. And if that's true, there are 100, 200 billion stars in the Milky Way galaxy. It's a lot of planets. Yeah. So planets are pretty common apparently. So I do have one more slide because we have an eclipse coming up. I feel like I'm obligated, and so I'm obligated to give you what you already know. All right, that's really it. Thanks.